Motion of a charged particle in a magnetic field. Consider a positive charge Q moving in a uniform magnetic field B. It will experience a force called Lorentz force, given by F is equal to Q into V cross B. This force changes the direction of motion of the charged particle. Let the angle between the velocity of the charged particle and the magnetic field be theta. The direction of force experienced by the particle is given by the right-hand rule, which states that if you curl the fingers of your right hand from V to B, then the thumb gives the direction of the force. Thus, the force is perpendicular to the plane containing V and B and acts in the upward direction. If a negative charge moves instead of positive, then, according to the right-hand rule, the force will act in downward direction, and the particle gets deflected in the downward direction. Let us study different possibilities. Case 1. The positive charge Q is at rest in the magnetic field B. It remains at rest as the magnetic field does not exert any force on a stationary charged particle. Case 2. The positive charge moves parallel or antiparallel to the magnetic field. It continues to move along the same line with the same velocity in the same direction, since the force experienced is again zero. Case 3. The charged particle moves perpendicular to the direction of magnetic field. It experiences a force in a direction perpendicular to the plane containing V and B. This force provides the centripetal force and makes the charged particle move along a circular path of radius r equal to mv by qb. We now consider three different charged particles: proton, deuteron and alpha particle moving with the same velocity v in the same direction in the given uniform field. As soon as the magnetic field is applied, all three of them start moving in a circular path. Since the radius of the circular path depends on the charge and mass of the particle, it will be different for different particles. Next, we consider an electron and a positron moving with the same speed in the same direction. On applying the field, they traverse the circular path in opposite direction due to opposite charges. The charged particle moves at an angle theta to the magnetic field. The velocity v can be resolved into two components: v sin theta perpendicular to the field and v cos theta parallel to the magnetic field. Due to the perpendicular component of the velocity, a force F acts perpendicular to B and to v sin theta. This force causes the charged particle to move along the circular path. Due to the parallel component of the velocity, no force acts on the particle and it continues to move parallel to the magnetic field along a straight line with the velocity v cos theta. The combined effect of linear motion along the field and circular motion in a plane perpendicular to the field is helical motion, with the axis of the helix along the magnetic field. A helix is characterized by its pitch and the radius. Pitch is the linear distance covered by the particle along the magnetic field in one complete cycle. As the angle theta between the velocity and the magnetic field increases, the radius increases as it depends on v sin theta, and the pitch decreases as it depends on v cos theta.